Did you get the talk to?
I did, yeah.
Yeah, you did. Okay. Oh, it's okay. What a good choice. You're so reverent. So
All right.
yes. Is that what it is? Yeah. You're not going to be asking questions.
All right. Welcome everyone to the Condensed Matter seminar. So today we're happy to have Jiadong Zhang visiting us from University of New Hampshire. Jiadong got his PhD at Fudan University, and then he went on to Johns Hopkins, working with Oleg Cheryshev. And then from there, right to UNH, where he has now recently been promoted to full professor there. Yeah. Jiadong is an expert in exotic forms of magnetism, where the magnetic moments make really interesting, complicated swirls in real space, or make electrons do really interesting, complicated swirls in reciprocal space. So all kinds of forms of textured or topological magnetism. And I guess he's going to tell us about that today.
Okay. Thank you very much for the introduction. It's my first time receiving applause for being promoted. Okay. So today I will be talking about our research on topological spin textures, skyrmions, and hopfions. I have been in this field for more than 10 years, but still we see some interest and some new developments in this field. But before that, I know that everyone has your own hobby, especially some new hobbies developed during pandemic. And this, So what I did during pandemic is develop a raised bed in my backyard. So there are a lot of tomatoes, and there are also some squash here, and this is one harvest. A lot of tomato and eggplant and a little bit beans, and there's another harvest. Yeah. It's more productive than my research. But I found this has very interesting physics, because this squash is a so-called climbing planet. It has stems reaching out to grasp everything it can reach. So if we zoom in here, you see there are some curly stem, and we call it tangent, and they have the fixed chirality. And this is the zoom in. But sometimes there is a conversion of the chirality, and this is so-called tangent pervasion. And there are some science papers on that. And so don't be surprised that in the future, if I get tired of the skyrmions, I will move on to this field. So for skyrmions is a topological texture, and anything about topology of magnetism can be traced back to the topology of magnetic ring. So if we just focus on a magnetic ring, if we allow all spins pointing in the plane, there are actually two topologically distinct structures. One is the spin polarized state, and the other is the vortex state in which the spins are playing out. And if you want to transfer from this vortex state to the spin polarized state, what you do is to keep this north pole unchanged and rotate this spin by in the counterclockwise direction by small angle. Then this angle gradually increase if you go on, and as a result, you will see that the spin to the left of north pole rotate by angle of 2 pi, while the one to the right rotated by just the infinitesimal angle. And the rotation angle is not continuous across this north pole. And there is no continuous deformation from a vortex to a spin polarized state. So they are topologically distinct. And this can be generalized into 3 dimensions. And again, there are 2 topologically different structures, spin polarized and this other fan-out state. And especially this fan-out state, we call it hedgehog state. If you view this magnetic moment as the magnetic field originated from monopole sitting at the center, and the spin polarized state has no monopole involved due to the Gauss law. The presence and absence of the monopole somehow indicates their topological difference. And this hedgehog is intimately related to skyrmion. And what you need to do is just to place this hedgehog on top of a 2D plane. And for any point on the sphere, you just project it onto a point on the 2D plane, on the same line connecting to the North Pole. You just project out, and you will see that the result is you get a structure like this. And this is a hedgehog state. If we rotate all spins about the axis by an angle of 90 degrees, you get another type of structure. And they are 2 typical skyrmions. This is so-called a block skyrmion, and this is the neo-type skyrmion. And this is realized in bulk materials, and this is realized in magnetic multilayers. And there's, as a topological index, there's also topology. As a topological structure, there's also topology index. We still start from the magnetic ring. The topological index will be the total angle this spin rotated while we traversing the ring. We just integral over the total angle, then divide by 2 pi. It will be integer. 0, 1, 2, so on and so forth. So in calculus, everyone, the instructor will tell you that the total derivative can be discarded. But from the topological perspective, it is very, very important. And for a magnet, for this hedgehog state, you just do the same thing. Instead of integral of the total derivative angle, you just integral of the total solid angle. And solid angle has unit of 4 pi. And then this measure can be written in terms of theta phi, the polar and azimuthal angles. And for a skyrmion, this theta and phi, they depend on the position. Right? It's a function of x, y, and you just change the measure to x, y, and you end up with this nice equation. And this is so-called a topological charge of a skyrmion. And this will be only integer value. And skyrmion has been realized in real materials, this manganese silicide. This is neutron scattering, small angle neutron scattering, and this is helical state, this is conical state, and this is spin polarized state. And later in the next slide, I will show their structures. And this small pocket at finite temperature and finite magnetic field is the A phase. So that time A for anomaly, they don't know what is going on, but in this year they did a neutron scattering and resolved that it is the skyrmion crystal phase. And this was later confirmed by a real space image in terms of Lorentz transmission electron microscope on iron copper silicon. And so each round object is skyrmion, and they're closely packed into a triangle lattice. So the physics of this manganese or iron copper silicon can be captured by this simple Hamiltonian. The driving force behind the skyrmion physics is this Dzyaloshinskii-Moriya interaction. So this is the usual Heisenberg exchange. Want to promote the parallel spin configuration, but for this configuration, they want the neighboring spins to be perpendicular to each other in order to minimize the energy. And the result, as for their competition, neighboring spins will form a small but non-zero angle with respect to each other. And in this case, you will get a helix, the squash state that I mentioned. But if you apply the magnetic field, it will, at a very large magnetic field, all spins just align. But in between, there will be a conical phase. So this explains these three phases that I mentioned for magnetic side. But a skyrmion will be an emergent phase at finite temperature and a finite magnetic field. And after the discovery of skyrmion in magnetic side, there are a lot of materials discovered that can host the skyrmion. Most of them belong to this so-called spintronic compound. They share the same structure. Like this one, it's a little complicated, it's multi-ferroic, and it's insulating. And iron germanium is the largest, highest Curie temperature in this family so far, 280. And also there's also a magnetic multi-layer realization of the skyrmions, but they're near-type skyrmions, as I mentioned. Skyrmion also has very interesting dynamics. The dynamics of magnetization can be described by the so-called Landau-Lifshitz-Gilbert equation. So there are several terms here. The first term here is the Lamont precession. This term describes the spin transfer torque from a current in the magnetism. And this U is given by this quantity, and this J is the current density. And magnetization, here the polarization. This term describes the so-called non-adiabatic spin transfer torque. So the physics of the adiabatic spin transfer torque is there's a current coming, and the current always the electron the spin of the itinerant electron always want to be parallel with local moment, and so there is a influx of angular momentum. And this drives the rotation of the configuration and the motion of the texture collectively. But they are not necessarily always parallel with each other. And the itinerant electron might have the spins not parallel with the local moment. And this can be phenomenologically captured by this equation. And the last term is this Gilbert damping term. It just shows the local moment could interact with electrons, and electron will dissipate through Joule heating, and this is the energy dissipation. Everything is captured by this. We are interested in the dynamics of the skyrmion, and dynamics of skyrmion can be described by the dynamics of its displacement. And the magnetic moment in space-time RT can be described as a collective shift of the stabilized skyrmion configuration by an amount of up. And all the time dependence will be attributed to a time dependence of this displacement. So for example, we plug in, and this term, we can just write in terms of chain rule. And kind of vaguely speaking, and so this is a low-lying dynamics, but this is a fast mode. It's very spatial dependent. So we'll integrate them over the unit cell of the skyrmion. So with this treatment, eventually you will end up with the effective equation motion for the skyrmion. V here is the velocity of the skyrmion. G is the so-called gyrotropic tensor. It's along z direction with amplitude determined by the topological charge. Beta, alpha are these two parameters. So let's try to understand this, the consequence of this. The consequence is G, as I said, is topological charge is always plus minus 1 for skyrmion. But alpha, beta, they're in general very small. So if we just look at this term equals to 0. That means the velocity of the skyrmion is almost the same as u, which is proportional to the current density. But then we include this as a perturbation because of this cross product. This perturbation will lead to a transverse motion of the skyrmion. So there is a Hall effect of skyrmion once it's driven by a current. And this transverse velocity is proportional to Q, the topological charge. This is our recent collaborative work with the experimental group. We looked into copper manganese zinc, apply current in this direction, and this is a collective motion of the skyrmion. Yes.
I'm sorry, I just want to catch up for a second here. So U is the drift velocity of the electrons?
U is can be understood as drift velocity of the electron.
So it's not the Fermi velocity or something.
Not Fermi velocity. Yeah, but it has the same order of magnitude as the drift velocity, but not exactly the same. Yeah, because you can see that it has some definition depending on the magnetization. But of course, usually this P times mu B has the same order of magnitude as the MS. So they cancel out. It's almost the same as Q.
Okay. Thank you.
So you see that you apply a current in the x direction. It moves almost in the x direction, but has a y component velocity. If we analyze the trajectory, we can just focus on these two columns, A and C. They have the same direction of the current, but their topological charge of the skyrmion is opposite. So the skyrmion topological charge, I should mention here. So its topological charge is proportional to n dot partial xn cross partial yn. So you see it involves 3n, n is the magnetic moment. So if you reverse your magnetic field, and n will be reversed. As a result, this Q will be reversed. So this is what we did. We reversed the magnetic field, introduced the skyrmions with opposite topological charge, and you see that their longitudinal velocity is the same, but transverse velocity is opposite. So this is opposite the skyrmion charge. So this is the case with the free motion of skyrmion in a two-dimensional plane. In principle, there is also a phenomenological force every time that if the geometry is constrained. If it's transversely constrained, then there is a transverse velocity, a transverse force, and this force would cancel with this gyrotropic term. As a result, you only have this term remaining. And if this term equals to 0, what you expect is the velocity of the skyrmion will be beta over alpha times u. Beta is non-adiabatic spin transfer torque. Alpha is the Gilbert damping. They're both small, but their ratio is not necessarily small. And this can be enabled by placing skyrmion in a very narrow ribbon. Yeah.
That's what I want.
Yes.
Okay, thank you.
Yeah. So, but what we did is another approach. our approach is the following. There's a notch here, and this notch could help facilitate a skyrmion. But these lengths are helical lengths. So by special design of the notch, we can place a skyrmion in between neighboring helical lengths. And these helical lengths provide the geometrical constraint in the transverse direction. All right, so yeah, and maybe I should show that again. You see that this skyrmion is generated by the notch, and then it keeps moving. And we can analyze the velocity. The velocity is still a function, a linear function of the current injected. But if you compare the slope of Vj curve, so this is what I showed in the previous slide, the free motion of skyrmion 2D, and there Vj, this slope is about 1, up to 10 to minus 10 or whatever unit. But for this one, this slope is 8.3. So that means given the same structure, given the same material, if you use this structure, have the skyrmion confined in the transverse direction, the velocity would be almost 1 order of magnitude higher than free motion of skyrmion. Yes?
Sorry, just to clarify, so the stripes correspond to a helical
length
structure?
Just the helical length. If you you apply, you don't do anything, and this is I think this iron germanium, and there's automatically some helical lengths generated in the sample.
And then the little notch just makes a concentrated magnetic field.
The little notch is introduced in order to inject a current through the notch.
Current, okay.
Yeah.
What do you mean by helical length?
Helical length is
Helical length.
is just like I should have mentioned that. So this is the helix. As I don't have the. Let me see what I have. Picture here, maybe not. Yeah, I don't. So just like this. There's lengths in this direction. All the spins they're just pointing in the same direction, but here in this lane the spins pointing in that direction. Here the spins pointing in the same direction, and here the spins pointing in the opposite direction. And if you view this along this line, and the spins are just rotating up, they're spiraling up. So this is the helix. So the Q vector of the helix is here, perpendicular to the lane. But we can have the skyrmion moving within this lane. So this is the basic structure of that. Any other questions?
There seem to be different intercepts between 2D and 1D. Is there any information to be extracted there? There's intercept that's non-zero for the 2D.
Yes. So in 2D, the skyrmion start moving at low current. But once it's confined in 1D, although the velocity is higher, there is a problem because the skyrmion can be easily pinged by local impurity. You need a little bit larger field, a larger current to drive the motion of the skyrmion. But once it starts to move, it moves quickly. So this is the point. Yes.
What if you have some disorders along the way?
Yeah, if there is disorders, then this threshold current will be shifted to the higher value.
Okay.
Yeah, you need a higher current to drive the motion. But this is the first time we reach the velocity of skyrmion almost close to one kilometer per second. So this is the fastest velocity of skyrmion ever.
At large current densities, right?
Yeah, and large current density.
Okay.
Yes.
These are really high.
It's decently high.
Okay.
Yes. If the current is even higher, then the skyrmion will move across the lane, because the larger the longitudinal velocity, the larger the transverse velocity, and the skyrmion will jump from one lane to the other. Or if your current is really very high, then the skyrmion will be annihilated. So there is a window here. And we also did some first principle calculations through modeling, and we confirmed that iron germanium has this beta over alpha ratio that is very large, almost close to 10. But for all other conventional ferromagnets, this ratio is about 1. So there is really a gift, I would say, from the iron.
So if you have a bilayer structure without this crystal, do you still have the same formula for the velocity?
Bilayer is different. Bilayer is driven by spin orbital coupling. So spin orbital torque. Spin orbital torque, that is Lucas' business. And Lucas is not here. Lucas wants to hold the record of the velocity, but we break the record.
So the velocity is not beta over alpha.
It's not beta alpha. It's 1 over alpha.
1 over alpha.
Yes, yeah. If they're doing a good job, probably their velocity can be even higher. But the stability is another issue. So this is more stable.
This is faster than Usain Bolt. It's amazing.
Yeah, but it starts slowly.
Start slowly. Yeah,
Yes.
Usain's really good at it.
Yes, yeah, you need a lot. But what I really want to talk about today is the three-dimensional topological spin textures. So we'll start with the discussion of three-dimensional skyrmions. Skyrmion is, mathematically, it is well defined in 2D. The spins rotate in 3 dimensions, but the base manifold is still 2D. But in 3D, there are still a lot of interesting configurations, like this skyrmionium. There is some prediction of skyrmionium. This is skyrmionium. The difference compared to the conventional, this is skyrmion, and this is skyrmionium. And so for skyrmion from center to peripheral, this spin rotated by an angle of pi. Center pointing down, peripheral pointing up. They're pointing opposite to each other. But for skyrmionium, center pointing up, then down, then up. If you use the color plot to stand for the in-plane magnetic, in-plane magnetic direction, and the skyrmion can be described by this disk, and it has topological charge of -1, and this sign is this minus sign is because the center spin is always pointing opposite to the external magnetic field. Your peripheral spins want to be parallel with the external magnetic field. Center spin is opposite. And we do the same plot for skyrmionium. And it can be understood as the central skyrmion wrapped by a circular disk. And this circular disk has topological charge 1. And as a result, skyrmionium has 0 topological charge. And this can be generalized, and there are more and more concentric helical lanes. And this is what we call a target skyrmion. This target skyrmion can be realized in a magnetic nanodisk, a iron germanium nanodisk. So we did some simulations, show that this is the top view, this bottom view, and the side view. So there's a skyrmionium that can be stabilized in a iron germanium nanodisk with a finite height. And this can be even stabilized in the absence of external magnetic field. Geometrical construction is a good thing for the formation of this complicated structure. Since there is no external magnetic field, two configurations that are time reversal to each other share the same energy. This center spin down, then up, then down, or center spin up, then down, then up. They share exactly the same energy. So there are two types of skyrmionium, and these are also realized experimentally by this electron holographic measurement. But this skyrmionium is confined in the disk. We are interested in the skyrmionium that can freely move. So this is our prediction. If we again see this skyrmionium as the central skyrmion wrapped by a circular helix, if we see this circular helix as back, it should be able to contain more and more skyrmions inside. And this is what we call a skyrmion bundle. And this skyrmion bundle can really be realized. We did this numerical simulations. What we did is we first applied a magnetic field in the minus z direction. Then we under this magnetic field, there are some skyrmion formation, and the center of skyrmion, as I said, is pointing opposite to external magnetic field. So center skyrmion is pointing up. Then we gradually turn off the field, and most of the skyrmion gone, and they're replaced by helical links, because helix is more stable at low field, zero field. Then we gradually turn on a positive field. But this skyrmions with center spin up is not stable under a positive field. Most of them will be annihilated. But still there are a little bit, there are some skyrmion remains. And this skyrmion remains because they are wrapped by a helical link. So this helical link provided back support the presence of these skyrmions as inside. So this is a kind of non-equilibrium realization of the skyrmion bond. This is the experiment. Yes.
So skyrmion, it has a charge equal to 0.
Right.
But does it still enjoy the topological stability or robustness? Is it easy to destroy it?
It is relatively difficult to destroy, but compared to skyrmion, it's of course more fragile.
Okay. Also, can you, on a single particle, generate a charge equal to 2 instead of 1?
Yeah, charge equal to 2, then you need to do more work. And this skyrmion bond, so you need to have more skyrmions inside.
But this is multi-particle. Each particle is a charge equal to 1. But can you have a single particle with charge equal to 2?
Yes, you can. But I don't know whether there's any experimental realization. So this topological charge, you remember we have this sin theta d theta d phi. This is another way of writing topological charge. And this sin theta d theta, you can just write in terms of minus of d cosine theta d phi. So if you have a configuration,
Oh, you cannot write down that. No.
Is that this wall?
It's wall.
It's what?
Yeah, wall is wall.
No.
It's not. It's a blackboard, a whiteboard.
It's whiteboard.
Okay.
Just
Okay.
pull the board down afterwards. That's
So this is a configuration from center to the peripheral. This, if you just focus on the change of nz,
Yeah.
this is equals change of cosine theta. Right, so this is responsible for this part. But then you're traversing around this configuration, and you see how your spin rotate, how your in-plane spin configuration rotate. If your in-plane spin configuration delta phi rotate by n times of 2 pi, then your topological charge will be n.
Okay.
But for most conventional skyrmions, you traversing around the skyrmion, this will just rotate
Just 2 pi.
angle of 2 pi. So you only have 1 plus minus 1. Yeah. But this is another way to realize high Q state. And this is the experiment exactly did the same thing. And eventually end up with a skyrmion bundle. But there were 6 skyrmions inside. So I would say that the number of skyrmions in the bag is completely random. But what you can do is, like here, there were 17 or 18 skyrmions inside. Starting from this configuration, you gradually increase your field. And there's a cascading topological charge change by annihilating skyrmions inside one by one. 17, 16, 15, and this is stepwise. Eventually, you get a skyrmion with topological charge 0. But if you further increase the field, this central skyrmion, because as I said, it has a central spin configuration, a central spin pointing in the same direction as the external magnetic field. It's not stable, it will be collapsed. And eventually, you end up with a conventional skyrmion with a central spin pointing opposite to the external magnetic field. Has topological charge -1. Yes.
So I see how it falls apart. Do they move? Do single skyrmions move together to make this raft, or do they all grow next to each other?
There is a chain of clustering of the skyrmion.
So they can start separate and then.
They want to be close to each other. You're asking this one or?
Well, so there's 17 there. Were there 17 individual ones that were far apart and then they coalesced, or did they form all in the same place?
They originally they were in the same place. Like here, there's multiple skyrmions. If there is a lock, this helical lane wrap around, then this would end up with a skyrmion bundle.
I see.
Not all skyrmions from different places they come together.
Got it.
This is unlikely.
Okay, thanks.
Yes.
Is there, when I look at how the topological charge changes with fields, sometimes it jumps by 1 and sometimes it jumps by 5 or 2. Is there any meaning?
What is the energy scale that
Yeah.
matters here?
Is this just one measurement that happened once, and if you were to repeat it, then between 10 and 5, it might do steps of 1? Or...
This is my collaborators' Lawrence TM measurement. Lawrence TM measurement is not continuous, so they take the image every several seconds or minutes. So it's likely that in between this, in between 2 measurements, there will be more transitions, and we failed to capture that.
But for the same change in field, there's sometimes much larger changes.
Yeah.
So what determines the strength of the topological protection, right? The charge, when the charge changes, that's when you're violating the protection or you're overcoming the protection.
Yeah, I would say that it depends on many details. Basically, we have in the energy landscape, there is a barrier. And the stability of the skyrmion obeys the Arrhenius law. And this barrier will depend on many things. It just depend on details.
So is it correct to say that over there you do have a Zeeman scale that's roughly 0.2 Tesla, 200 millitesla? That's where most of them collapse, and that's the characteristic of the barrier that you were mentioning.
I would not say that. Yeah, I would not say that.
But also the first ABC are measurement, and the D, the color, is that measurement or is that simulation? Like you added.
This is a measurement. So this is so-called
Lorentz mod detector.
TIE something.
Okay. So you already has a spin direction for each location.
Right. So this color stands for the in-plane spin directions.
This is done at room temperature.
This is low temperature. This is iron germanium. Iron germanium has 288 Kelvin transition temperature. But I will say that there is still some three-dimensional structure. So this is our simulation. Inside, it's what we expected. There are some skyrmions wrapped by a helical link. But on the top and the bottom surface, the central skyrmions, they're melted and end up with this chiral vortex. And this is exactly kind of realization of this picture. Because you travel around, the in-plane spin directions rotate by multiples of 2. But the topological charge is still the same, layer by layer. And in recent work, we also show that there are some other exotic skyrmion-related textures once this iron germanium has tetrahedral geometry. So this is the collaboration with Topological group. They did the electron holography measurement with the electron beam in 3 different directions. And they get these images. And we did the magnetic simulations and confirmed that there's a zero field skyrmion stabilized in this 100 nanometer scale tetrahedron. And this skyrmion originated from the center of the bottom edge all the way up and end up with the center of the opposite edge. So yeah, there are 3-dimensional configurations. The problem is there are many configurations sharing similar energy, and we literally need to have a lot of effort in determining the right configurations. But these are just some warm-up. What we are mostly interested in recently is to find the true 3-dimensional topological spin textures. These skyrmions in 3 dimensions, they're not. They're not truly 3 dimensions. It's still a kind of a stacking of these 2-dimensional configurations. And the true 3-dimensional topological textures, you may say just this hedgehog that I mentioned. Hedgehog, it does have 3-dimensional nature. But the hedgehog has a singularity in itself. It is in the energy of vortex in 2D. I think here there are the work on vortex is very famous here, so I'm not going to talk too much about vortex. But this vortex is a defect configuration. And so hedgehog is a defect. What I want is a 3-dimensional topological spin texture By texture, I mean a configuration that is free of singularity. And the skyrmion is a texture. There is no singularity. Every position, the spin direction is well defined. And the right three-dimensional spin texture is the hopfion. So let me try to construct the hopfion. The skyrmion can be constructed by the stereographic projection that I mentioned. So for any point P prime on 2D plane, if it has coordinate x, y, you draw a line, connect to the north pole, and this P, OP has a direction of N1, N2, N3. And mathematically, if you learn the mathematical physics or some complex analysis, I think that this kind of equations were there. And if you just focus on the z component of this n, when r is 0, this is -1. When r is very large, it's +1. So that shows the center point down, peripheral point up. So this is the right skyrmion configuration. And we want to generalize into 3 dimensions. And what you do is, this skyrmion, this mapping is from R2 2D plane to S2, a unit sphere in 3D. And you just escalate dimension by 1 on each side. And this is the stereographic projection from a point in 3D to a point on the unit sphere in 4D. What do? Copy this, copy that, copy the last term, and then make up this new term with the denominator, with the numerator replaced by z. That's it. But we want spin configuration. And the spin as a unit, it's a unit vector. It must align on the unit sphere in 3D. So we need to further find a mapping from S3 to S2. And the answer is just quantum mechanics. You have these 4 numbers, you make up a spinor like this. And since pi 1 square plus pi 2 square plus pi 3 square plus pi 4 square is 1. And this spinor is automatically normalized. Then you calculate its expectation value, the expectation value of Pauli matrices with respect to this spinor. And this n is also automatically normalized. And this is the configuration we want. So for example, by this way, and you can end up with a configuration like this. And this is the hopfion configuration that we are looking for. Later I will show you what does it look like. And then topological index. Topological index of a skyrmion is, as I write down there, n dot partial x n cross partial y n. If we write down, write in terms of components, it will be like this. And these epsilons are total antisymmetric tensors. N partial n. And you can generalize it. You just make another partial fact. Total antisymmetrize everything. Then this is the topological index of the hopfion. And you also like to write in terms of some emergent magnetic field, and for this one, it will be integral of this. Now let's take a look of this topological index. Okay, so what does it mean? For any spin, if we choose some direction in 3 dimensions, if we find all the spins pointing like here, if we find all spins pointing in the negative x direction in the hopfion, and this, since hopfion is a texture, no singularity, this equals spin positions, they will form a closed loop. On this loop, all the spins pointing along negative x direction. And this loop, we call it pre-image. And you can find another direction, say positive x direction. Find all spins pointing in that direction, and they form a closed loop as well. And these two closed loop will be linked to each other. And this is this topological index about. So this is the linking number. If you assign more spin directions, find all of them pointing in that direction, and you see that this pre-images is getting larger and larger. And eventually, all the spins pointing in the equator, that means all spins with zero z component, will form a torus plane in 3D. So this is this cartoon spot. On this torus plane, all spins has zero z component. Different lines with different in-plane directions, and they're all linked to each other. Two arbitrary directions, you find the pre-image, they're always linked to each other. This is still a little bit confusing. What you can do is, let's take cross sections of this hopfion configuration. This plane cut through the torus plane, and you rotate this plane, and you will see that each cross section is just a skyrmion, but with their spin directions rotated. Like this one, it is eventually like a neo-type skyrmion. And for this part, it is a block-type skyrmion. Or that means from a skyrmion tube, what you do is you twist it. You can twist a skyrmion tube and connect two ends, and you will get a hopfion configuration. So this is a very complicated three-dimensional distribution of the magnetizations. The point is it can be still realized experimentally. So this is our prediction. So this is one of the first prediction of magnetic hopfion. I just showed that a iron germanium nanodisk can host a target skirt. But once this nanodisk is sandwiched in between two spin polarized layers, and then as a result, there will be hopfion inside. And there are some X-ray measurement on this kind of setting, but they choose a different realization of the skyrmions inside. It's just they use the magnetic multi-layers, but the idea is the same, and they confirm that there is a hopfion configuration inside.
What is sorry?
Sorry.
Yeah.
So you need two kinds of anisotropy. One is the PMA, and in the middle, you need what kind of anisotropy?
In the middle, you don't need to do anything. It's just iron germanium nanodisk with a fine-tune of thickness.
So the complexity is introduced by adding the surface anisotropy.
Yeah, because you need to polarize the spin far away from center to the same direction. Yeah. So that's why we artificially design this structure. But our goal is still to find a material, especially a single crystal material. You don't need to do anything. Don't need to design this artificial structure. And the ground state is just that complicated structure called hopfion.
Just so this is about, I guess, that experimental picture. Is the hopfion realized in a heterostructure that's composed of multiple versions of the heterostructure that stabilizes?
Yeah, because
so you just stack them on top of each other.
yeah, they have the same stacking sequence, but the thickness of this cobalt layer is different.
And then the hopfion extends through many layers.
Yeah,
right?
inside, yes, through many layers. And in this layer, for this, in the top layer for this combination, and there's a large anisotropy. So this part is basically polarized. but inside loss is complete distribution of spin.
Are you able to make hopfions with higher numbers of twists?
In principle, yes. In principle, yes. But we haven't had any luck in getting this. Yeah, but just like skyrmions, the skyrmions most stable state is Q equals to ±1, not ±2.
Then, so if you make skyrmions inside a material, then they can move around until there's enough density of them that they form a lattice.
Yeah.
Because they interact, they have some effective interaction.
Yes.
Do the hopfions, if you could also realize that inside of the material, then they would move around in 3 dimensions.
Yes.
And would they also have
Exactly.
some
Exactly. So I have kind of. I always believe that a stable hopfion must, in the single crystal, must be a multi-Q state. It must be a multi-Q state. But the question is, how shall we distribute these Q directions? And how can we find a material realizing this multi-Q state? This is the problem.
It must be a multi-Q with the star having more than 3.
More than 3.
And they must
non-coplanar.
Non-coplanar.
Yes.
Q, yeah.
So like skyrmions was theoretically predicted in 1990s, but the whole business of skyrmion start to develop after people found this killing material, manganese silicide. I think for hopfion, we are waiting for this material to be discovered.
But in manganese silicide, there was the anomalous phase.
Yeah, yes.
Are there any materials that you're aware of that have new anomalous phases?
And that's my question to you. Do you have any material you mark a phase inside? Then we can do some modeling.
You can already consider that's a single crystal, right? Because you have a superlattice.
That's not single crystal.
But it's just
It's just
one
combined.
hopfion.
Yeah.
So we're going to put lots of those together to make a hopfion
Yes.
lattice.
Yeah. So I'm leaning towards the idea that maybe we should look into a frustrated magnet with DM interactions, with some non-central symmetric frustrated magnets, because this hopfion breaks inversion symmetry. So we need some elements to break that symmetry.
Is there any chance that a hopfion can break down into something else like skyrmion?
Maybe like this one, if there is a evolution of the magnet anisotropy, and there will also be evolution from the hopfion to the skyrmion. Yeah. But mathematically, they're described by different topological index. And hopfion has this linked pre-image. You need to unlink that in order to make a topological triple and get into another topological class classified by the skyrmion index. So last piece is the dynamics. And hopfion also has very, very interesting dynamics. And there are 3 dimensions. So the dynamics in 3 dimensions. So we put a hopfion here. We apply a current, and we model this LG equation, and we found this hopfion moves. But you see, this torus plane is rotating. And also it has some transverse velocity. So there is a hopfion Hall effect, and there's a hopfion rotation during driven by this current. So this is the case with this beta smaller than alpha. Beta is the non-diabatic spin transporter, alpha is the Gilbert damping. If beta is larger than alpha, we do the same simulation, apply the same current, and it moves the same longitudinal direction, velocity, but opposite transverse velocity and opposite rotation direction. In a very special case with beta equals to alpha, this hopfion moves straight without any Hall effect and no rotation. We also model that in terms of this collective equation motion. I will just skip that. Yeah, I really should skip that. So, but finally, we end up with this equation motion for the hopfion. It's complicated, right? So theta x, theta y, they're just rotation angles. X, y are the transverse, transverse, just the displacement of the hopfion. And in a very special case, if we apply current perpendicular to this torus plane, this hopfion will move and it start to expand. If you apply a opposite current, it just shrinks. So this can also be modeled as well. Last message is we are seeing some interesting configurations in 3D. And the three-dimensional spintronics is about to come, but I don't think a lot of experimentalists in this room are ready to work on that because we don't have the right three-dimensional imaging tools. So three-dimensional magnetic reconstruction is very, very important. There are three-dimensional magnetic reconstruction in terms of soft X-ray. And in this effort, we are trying to develop a three-dimensional magnetic reconstruction in terms of electron holography or transmission electron microscope. And we did some machine learning things and tried to reconstruct the configuration, and the result is pretty good. So there are a lot of things that we can do to develop some techniques in order to resolve three-dimensional structures.
Can you use neutron deflection if you have a lattice?
Neutron, yes, but the neutron has a lot of problem, low cross sections, and there also
do tomography, so you can image, but you can't image.
Can you image a lattice of hopfion?
Maybe. Yeah. Maybe we shouldn't, because we already took all your questions.
And also, I heard there's neutron optics. So you probably can do something, polarize the neutrons. Yeah. So X-ray, I will say that X-ray and neutron, they have problem that you need to go to these facilities to do that. But for TM, you can just do it. So this is the advantage. But there are still a lot of problems with electron holography. I don't want to say too much negative words about that. Yeah, there are some technical details. So with this, I like to summarize. I like to convince you that there are a lot of interesting physics in skyrmions, and also not only in 2D but also in 3D. And the hopfions is a new configuration that we really want to realize in the future in some single crystal materials. And this is a list of my collaborations. These are my students in UNH. Unfortunately, most of them, or maybe all of them, have left. I have some collaborations with Haifeng Du from Chinese Academy of Science, and they did a lot of long TM measurement and some theory collaborations. And so this work is mainly supported by DOE, and I spent 1 year sabbatical leave in Germany, supported by Alexander von Humboldt Foundation. With this, I'd like to thank you for your attention.
Okay, we already took up a lot of time with questions, so maybe there's a couple very quick ones. Questions? Okay, well.
Can I ask you a quick question?
Wait, we have a student question at the back.
Yes.
So you discussed studying the dynamics of skyrmions, only considering the center, like the motion of the center of it. Are there ways, like, and that was driven by a current, are there ways to influence, say, the structure of a single skyrmion like change its diameter or other dynamics?
Yeah. So there is, and once the skyrmion moves, there's a breathing mode, the diameter, the radius can change, and with this dynamics, the skyrmion will acquire a mass. So this is the main origin of the mass of the skyrmion. So this is very, very important actually.
Yeah, so by increasing color, you say the skyrmion hopfion gets bigger,
Yes,
smaller.
right.
So can you, and then the size is you can measure using anomalous Hall effect.
Mm-hmm.
So can you use that technique to identify hopfion? Skyrmion doesn't have this property, right?
Yeah, maybe. Yeah, I think that. Yeah, but you need to have very fine design of the electrode.
Yeah, electrodes.
Yes.
Can you do it if you had a hopfion moves in 3 dimensions, so it should curve in two directions. The skyrmion is a tube that should only.
Yeah. So the real dynamics is a combination of these two. So you have a hopfion like here. You apply current. What happens is it moves, but then it rotates.
Yeah.
Then it rotates all the way to the direction that is perpendicular to the current. Then it starts to expand, and then disappear. In my simulation. Yeah, but so that there is this also the hopfion lattice will be very important. Maybe with the lattice, this doesn't expand that much.
Okay. Thanks very much, Jiadong.
Jiadong. Nice talking to you.
Okay, thank you.
Yeah.
Yes.
Is the spintronics or?
I think that for the 3D, because so skyrmions, you can use them to carry information.
Right.
You use them for memories, so these racetrack memories,
Right.
belong to the tracks.
Yeah.
But they're just in 2D, so the information density is not all it could be. In 3D, I guess you can have these little blobs that could be packed in 3D, and then the other interest is just it's like a really weird structure.
Yeah, I remove a lot of introduction slides, so maybe this is not a good idea.
I thought actually their introduction was like it was good. It was like a pedagogical introduction.
Yeah, I should have more helix, helix kind of things.
On website news.
A lot of people, would not show that. Like those simple pictures of the magnetic ring.
Preparation for next week's announcement.
Understand what you're talking about.
Yeah, because I invited Gang to give a colloquium in our university just 3 weeks ago, and he talked about skyrmion. I thought here there maybe already familiar with this concept.
No, mostly just non-screw.
Oh, okay, I see.
Right. Yes. So does this have to be spin? Could it be other type of ISIS spin?
Yeah, there can be electric polarization. Yeah, there is a